time tonight. We'd like to meet them. So after the meeting, why stick around if you'd like.
Okay.
We'll chat.
All right. Sounds good. All right. So observing. Andrew, your turn. Find your presentation here. Over here. All right, here's the slide advancer.
I think. All right, there we go. Hi, everyone. My name is Andrew Richner. I'm the observing chair for the DVAA, and this is the observing report for July 2022. And before I get into this, I do want to kind of go off what Jeremy was saying, how, the James Webb Telescope, very impressive. I don't think anybody doesn't think so. But it really only looks in the infrared. It looks from shortwave infrared to the longwave infrared. And from a sensor standpoint, you use different materials to handle that, from mercatel to gallium arsenide, but you kind of just stitch it together. And the thought about how you do that is the same. The way Hubble does ultraviolet all the way to shortwave infrared is just astounding to me from a sensor technology standpoint, because the way that you think about imaging each one of those regimes is completely different from each other. So I hope Hubble still, kicks around. There's a lot of science that Hubble can do. But I'm going to enjoy looking at the James Webb Telescope pictures anyway. So, all right, so into the observing report. And this month I wanted to look at Equila, the eagle. It doesn't get very high in our sky, but 2 months ago I did Cygnus. Last month I did Lyre, so I thought that this would be the logical successor to those. Being that the alpha star Altair, Altair right there, is part of the summer triangle, the big asterism in the summer sky. So a little bit of overview. Equila is one of the quote unquote oldest constellations. Now, what do I mean by oldest? Well, I think it was the Sumerians who first designated this group of stars as an eagle. And then that kind of just been passed down through all of the ancient civilizations to then us, really. So that's one of the few constellations out there that kind of kept its name, the eagle, throughout all of those generations. Dates back to 2600 BC. Now it is situated on the celestial equator, and you can see that it's down here, but I wanted to keep this image. It's down the lower part of the image for those of you online. But I wanted to keep this because it shows the Great Rift, and that's that big dark area in the Milky Way. So if we look at the summer triangle here with Deneb, that blue star right in the middle, and then Vega off to the right, and then Altair down at the bottom, you can see that giant rift in the Milky Way that you're in a dark sky location when you can easily see that in the sky, naked eye. Now, being in the Milky Way, it's kind of pouring open clusters, which, you kind of associate the Milky Way with the open clusters, and then the off Milky Way constellations of having globular clusters. Because the globular clusters are older, it takes a long time to form, and then the Milky Way has some younger stars on the plane, and then they would be in the open clusters. So being a Milky Way constellation, there's a poor amount of open clusters. However, it is very abundant in planetary nebulae, and I'll show a lot of good specimens of that later. And being situated to the Great Rift, there's also a good amount of dark nebula in the area as well. All right, so here's the star chart. You can see Altair, the alpha star up there. That's about 0.7 magnitude or so. So it's a pretty bright star. You can see this drawn different ways. I've seen just like a big kite connecting the four stars. I like it this way, how you can kind of bring out the wings to kind of make it seem like, hey, we're not just making things up out here. It actually does look like an eagle. But the first thing that you'll notice is there's not a lot of stuff in it, to be honest. Like there's not a lot of, like little yellow circles for clusters. There's not a lot of big nebula or anything. So a lot of these objects are going to be on the more intermediate to advanced objects. A lot of them will be definitely better for a telescope rather than binoculars. But there are some pretty interesting stars also, which I'll talk about, which can obviously be seen with binoculars or telescopes and even the naked eye. Now, one of the stars is Altair. So Altair, it seems pretty benign. It's just up there. It's a single star system. It's kind of like bluish white, but it's actually pretty interesting. Altair spins very, very fast. I put it up there in case anyone wants to know, 290 kilometers per second. How fast is that? I don't know. We don't go anywhere close to that. But what's interesting is that it is spinning so fast that it's actually not completely spherical. It is kind of squashed, if you will, along the poles, which makes it kind of interesting. Why is it spinning so fast? There's a lot of interesting research there. It is also one of the first stars to be directly imaged. And when I say that we have directly imaged the surface of the star and actually seen some resolved components like sunspots on the star. You can't see them in this image here, but it has been done. And the reason why that is because it is one of the closest stars to us. Even though it's not the brightest star in the sky, it is pretty close to us. All right, next is our Equila. And if you know my presentations, I really like stars, especially variable stars. So our Equila is a Mira type pulsating star. So what is that? That means that the star itself is actually changing size. It's pulsating, if you will. And why it's doing that is because it's actually changing in temperature. So when it is smaller in diameter, it's a bit cooler. And then when it's larger in diameter, it's a bit hotter. Now that causes the magnitude to go from 5.5 all the way down to magnitude 12 in about 284 days. But it's not really the fact that the light is decreasing from the star. What's happening is that as it gets cooler, light is moving from the visible range over here, so about 5,000 Kelvin or so. Well, 5,000 Kelvin is pretty hot for this star, but if you will, for example, 5,000 Kelvin, as you get cooler, you can see that the light moves more into the infrared. So we can't see that light. So it's not really that there's less light coming from the star, it's that the light's just shifting to a regime that we can't see. If you, for instance, put an infrared camera, like something like James Webb Telescope on this, I think you'd find that the actual amount of light coming from the star is relatively constant over that. It's just our eyes that can't see the light as it shifts through its period.
What's the timing of the cycle?
Excuse me?
What's the timing of those cycles of big and little?
284 days is going from like the brightest point up here to then the brightest point over there. It's about 284 days. So it's not really going to be something that you can directly observe. You'd have to keep going back to it over the course of the year, really, to see any difference. So, and then I just put up here for reference, this is from our friends at AAVSO. A lot of these, again, measurements are from amateur astronomers, just like you. You can, if you're interested in doing this kind of thing, you can go there and then it'll tell you all about how to make variable star measurements and then to report them and to actually contribute to real science being done, which is fun. All right, next we have 23 Equila. And I wish Bart was here, or maybe he's online, but this is one of the rare cases where you can see a green star. So this is a double star system. And it is described as a yellow and green pair. Now, you can't have a green star. They don't exist. If we look at this plot here, and I won't bore you with color science because it bored me in school, but if you look at this right here, this is called the Plonkian Locus. These are all of the colors that come from a black body. So like when you heat up a metal and you go and you keep heating it up, it will go from, red to yellow to white to blue. It's the hottest, as we observe it with our eyes. Green is not on here. Okay, stars can't be green. Stars are essentially black bodies. So how is this star green? Well, there is an optical illusion that if you bring, because the primary star is yellow, and then the secondary star is less bright, of course, and it's so close to each other, it's 3 arc-second separation, that secondary star looks green. And that's basically called color fringing. That's just an optical illusion that our eyes create. And it is because the primary star is yellow reddish, and then that secondary one is so much dimmer. So this is one of the rare cases that you can see a green star. And I wanted to put it up there because we've been talking about double stars for the last few months or so.
I used to hear that Altair also had a greenish cast at some point.
Mhm.
I realized that the green stars are rare, but I had heard that Altair was greenish, but
Okay.
your description said it was really in the blue.
So I would describe Altair, if we go back, definitely as bluer, being a type A7V star. So an A is going to be slightly hotter than our sun, and that would lend it to be kind of blue. Now, my theory, though, why it might be green is because, like I've said, it doesn't get very high. We talked about this outside, right? It doesn't get very high in the sky. And that can cause, when we're looking through the atmosphere, and so that can cause a lot of distortion as well. For instance, if you see those pictures of the Milky Way, like long exposures, you'll sometimes see a green hue along the atmosphere, along the horizon. And that's just from light being diffracted in the sky. So that's what I would guess why Altair might sometimes have a greenish hue. Yes, there.
There's a small companion star to Antares that's close, that looks green. It might be another one of these reflexive things, but if you look at Antares, it's not very high in the sky, but with the right conditions and the right telescope, it has a little green companion that looks green.
Okay, yeah. Well, Antares is a good one, yeah. And that would make sense because Antares is so red.
It's a reddish, it's a red star, but it's quite greenish to look at.
Okay, yeah, great. Yes.
You give it rotation speed kilometers per second.
Yeah.
How does that translate into radians per second? Circular.
Into radians per second? I don't know
Revolutions per second.
off the top of my head.
I think it's like 16 hours.
16 hours, is that?
Very fast.
That's pretty fast. Yeah. That's not in radians per second, but
Well,
kind of gives you a
revolution
sense.
is 16 hours.
Yeah.
Okay, so it's 16 hours. It's in reps. I can trade that.
Okay. I'll leave that stuff for the orbit analysts, so to figure out. Yes.
Does our sun rotate too?
Yeah.
Our sun rotates, but not this fast.
What's the speed of light?
I know, Mitch, do you know?
Yeah, 25 days at the equator.
25 days. And that's why when somebody points out sunspots or so, we don't need to immediately go out and look at them the day of. And we have the opportunity to look and see how the sunspots merge and move over time. Whereas if the sunspots on Altair, you need to get out there really quickly, you're going to miss them. So, but they'll come back around. So take your bet. All right. Any other questions? All right. So I think that's my last star. So there are some open clusters in Altair. This is a pretty nice one, NGC 6709. If we look at the Trumpler class up there, the 3, that's a Roman numeral 3, means that it's pretty loosely concentrated. The 2 means that the M means that it's medium richness, and then the 2 means that it's pretty evenly spread out across all stars magnitude-wise. So about all the stars are kind of the same magnitude. If you do the observing the astronomical league program for open clusters, you learn a lot about the Trumpler class, which is pretty interesting. But it's not really a naked eye object. You can see it in binoculars, but you're not going to be able to pick out a lot of stars, maybe the brighter pairs. But you really need a telescope for this object. Now, you can, though, get away with a pretty modest telescope, 4 inches or so. But it's going to be best in an 8-inch or larger to get a lot of those stars. And you can see from looking at the picture, you kind of have this like triangle grouping of stars there. So if you observe it with 4 inches, you're going to pick out, you're going to definitely get the sense that it's a triangle or so. You're going to get some of the brighter stars along the vertices. But if you go 8 inches or larger, you're going to get a lot more stars. It's going to be a pretty rich cluster. So planetary nebula. I mentioned that there's a lot of planetary nebula in Altair, in Equila. I can't really tell you why that they're there, but these are pretty challenging objects. Planetary nebula people think that they can be kind of easy because of the ring nebula. The ring nebula is very distinct. It's really easy to see the ring. But planetary nebula as an object class are pretty difficult. And these are all pretty small. So small that a lot of them, if you don't have a really big telescope, a lot of them are going to kind of look like stars, to be honest. And a nice trick that I tell people is to take a filter, either a UHC or O3 filter, and don't put it on the eyepiece. Kind of like get an eyepiece with a lot of eye relief so that you can move your head away, and take that filter and then kind of move it in and out of the field of view. And you'll see the stars just disappear, and then the planetary nebula will still stay there. Because the planetary nebula is emitting a lot of light that those filters allow through, but the stars aren't. So that's a great way to kind of, if you think you're in the area and you can't find the planetary nebula, then just bust out those filters and really increase that contrast. Yeah, but a lot of these are small. Again, I would not go hunting for the center star in these. You're probably not going to see them. 8-inch scope minimum, and then probably best in 12-inch plus or so. But very challenging objects, and they can be pretty rewarding once you see them. So this guy is NGC 6781. This would be a good one if you did want to see the ring structure, because it's pretty pronounced there. There's a lot of concentration of gas along the edges. And then here are some other examples. We have a 6772 up in the top left there. A Bell 70, which is kind of interesting. That reminds me of like the diamond ring effect that you get with like a solar eclipse with that background star kind of right there. And then down in the bottom right, 6852, and then in the lower left, 6804. Now, these are just a handful. There are probably about a dozen or so. And if you're doing the Astronomical League Planetary Nebula list, you're going to be in Equila quite often. All right, last I want to talk about dark nebula. And dark nebula, I've mentioned it before, but they're kind of overlooked. But it's basically just a lot of gas that is not allowing the light from the stars in the background to come through. Now, there is a classification of them, determining like how large they are, how transparent they are. But I didn't mention that here, but there's a lot of them out there. And it probably is no coincidence that there's a lot of dark nebula in the region, and also Equila so close to the Great Rift. So these aren't really imaged a lot, so I couldn't show a nice pretty slide with a bunch of pictures like I did last time. So I just listed a few here if anybody is taking notes or wanted to know. Bernard is pretty much the de facto dark nebula catalog. And I like this one here because it's the E nebula. And you can kind of see the E there, although it looks more like a C to me. Now, some tips for observing these. You're going to need a decent sized telescope, probably about 10 inches or so plus to observe these. I like to look at them with a pretty wide field of view, because the only way that you're seeing these is from the contrast and lack of stars. So if you can get a pretty wide field of view and then notice, hey, this is the concentration of stars in the area, and then these are the regions that there aren't any stars. Let me go check out those regions. It would just increase the contrast and you see more, so you can pick out these nebula easier. But these are pretty tricky. And there is an Astronomical League club for observing club for these as well. And my party picture here, kind of bringing the whole thing together, is a Bernard 139, this kind of dark area there. And this is a good example of how challenging these objects can be, because if you're not really looking for them, you're not really going to notice too much that there's a dark nebula there. But also right by is NGC 6778, which is if you look at like high resolution images of that, it's kind of like a little dumbbell nebula, which is pretty interesting. But here we have the two main objects in Altair, or Equila, sorry, right next to each other. So kind of neat. And that's my last slide. So thank you.
All right, thanks, Andrew. I'm gonna try to move this a little bit, get a little better views. John, you ready?
Sure.
All right, so now for our main presentation of the evening, we're delighted to have back John Conrad, who's a NASA JPL Solar System ambassador. So John did his work with the unmanned spaceflight program at the US Air Force and for NASA as well. And today he's going to be telling us about a new mission coming up, which is the DART, Double Asteroid Deflection Test. Let me bring the slideshow up here. Nope, that's the wrong one.
Alert, alert.
All right. So secure, it won't let me do what I want. Enable external content. All right. Let's do that.
Perfect.
All right. So
You got a
you may
clicker, or
So you may recognize John. He's given us a few presentations before. He's talked about lunar science. He's talked about Cassini. He's talked about rocket science 101. He's talked about global climate change, the view from space. And tonight he's going to be telling us about the double asteroid deflection test, which will be happening later this fall. Right. So John, take it away.
Thanks a lot, Jeremy.
As a reminder, if you have any questions, you won't be able to hear it on the YouTube, so please repeat any questions that may come up.
Okay.
All right.
So John talks a lot, I think, is basically what was just said there. It is better than you can imagine to be back and see all you folks standing here in front of you. I have talked to you a number of times in the last year and a half, I think, but all Zooming. And so the last time that I was here in person, this is what was outside. It was, is this not going to work?
Oh, I just have to diddle it to let it know that we're on that.
Okay, I didn't know how to diddle it. Okay. 2.5 years ago, or if you know your lunar month, 29.53 days, it was on Wednesday, exactly 31 moons ago. So many moons ago, I was here. A very memorable night for me. And here we go. I now call that the Ambassador Moon, which immodestly I will say I named after myself, because a lot of you may know that it was not only the last time I was standing here, but about 2 minutes after I walked out of the room, it was the last time I was standing, period, for about 2 months. I broke my ankle on the way to my car. So I will always remember you guys, and I will always remember this place. So I'm glad to be back, and I must say to the folks that are on YouTube, hello to you also. Hope to see you all again. So let's get on with it. So much for the nostalgia. And we'll start right off with a couple of famous astronomers in the front row there. And I'm going to guess that a lot of you saw this movie.
Oh, yeah.
And of course, the famous astronomers are famous astronomer actors. And the famous president, who didn't necessarily resemble anybody, was Meryl Streep there, except for the fact that she was the president that decided that not enough people cared about science, so she could just tell the population, don't look up, when there was a dangerous NEO, near-Earth object coming. And no matter how much the astronomers hollered and pointed, they didn't look up, which I must say, 7, 8 years ago, I would have thought was too improbable. But somehow today, with the attitude towards science, it sadly wasn't just funny, it was a little bit scary. So tonight, we're going to look up. And the whole point of this talk is to talk about how we are looking up at near-Earth objects, at an asteroid like this, with a spacecraft known as DART, which is the Double Asteroid Redirection Test. And it is a planetary defense mission. And we'll talk about what that office is and what their mission is, and a little bit about the threat. But mostly we're going to talk about what DART is about to do, because it's been launched, it's on its way, and pretty soon we're going to have quite a special event. Tarek Daly, I have to give a lot of credit to. He's one of the instrument scientists for DART. He gave these slides to us in a really good talk. And so I'm going to be using a lot of his material. And I wanted to just point out that this is an asteroid built by APL, Applied Physics Lab, which I don't know if a lot of you are aware of. They're not quite as well known as JPL, but they have built a lot of spacecraft through the years. In particular, on a personal note, as Jeremy mentioned, I used to be involved in the unmanned programs. I actually launched an APL satellite 54 years ago, at 68, from Vandenberg. And DART launched about half an hour from that site in November. And so the APL satellite that I launched was a very small one. It was in the first 10 years of the space age. We had about a dozen of these stacked above the upper stage in a unique configuration of an Atlas and a burner 2. And they all did great in coming off of the being deployed, except for the fact that the fairing never separated. And so we had a whole bunch of satellites inside the fairing going into the South Pacific about 20 minutes after launch. It was not one of the greatest days for the Air Force or for APL, but that's the kind of stuff that made life exciting in the first decade. So here we are today, and APL has had a number of successes like New Horizons. And this particular one, I want to give credit not just to them, but also to JPL, who played a major role in it. A whole bunch of NASA centers there in the upper left, and you're probably aware that JPL is not a NASA center. It's a contractor like APL is. And the centers, of course, have government employees. And then there are quite a number of national lab and universities and commercial companies that are also involved. The programs all fall under this brand new umbrella that I've talked about in my NEO talk, where we actually have a planetary defense officer reporting to the head of NASA, who's the senior official in the US for defending our planet. And they have quite a few functions that they perform. And in the last 10 years or so, all the major agencies around the world have set up one of these planetary defense programs. And one of the functions they perform, or I should say all the functions that are up here, they're trying to coordinate on. So let's just kind of look at what's up here quickly. In the center of the top is the place that keeps the information about all of these NEOs, the near Earth objects, especially what they call PHAs, potentially hazardous asteroids. So those are the ones, they all are the ones, and we have now more than 500,000 of them in the inventory at the Minor Planet Center, where they not only name them or number them and keep track of them, but they update their orbital elements on a regular basis, because perturbations can happen. And even though what they're doing with their computers is projecting the orbits of these, and everything like Earth goes around the sun, if it's not a moon. And so the orbits are on the order of a year to maybe 2 years, depending on what the cycle is, but they all pass across Earth's orbit. And what we're watching for as we look out literally decades into the future is any that are going to happen to cross at the same time Earth crosses there and have a potential collision. And so far, so good. Nothing of any hazardous size is projected with any, specifically any probability above maybe 1%, even decades out. So we'll keep an eye on all these, and the count is going up all the time. The upper right there is all of the surveillance telescopes, most of them on the ground, most of them doing what are called surveys. Well, they cover the whole sky over and over again, looking, putting things into the Minor Planet Center inventory. And then you come around clockwise and you find that we not only want to understand that these very dark, hard to see objects are there, but we'd like to know a bit more information about their size, obviously, but also about their shape, if possible, and some of their composition. So NEOWISE is a spacecraft that's addressing that, and Goldstone with a radio telescope and the infrared telescope are giving us some composition and shape information. So finally, down at the bottom there, you get to the point that with all these planetary defense offices, you've got exercises and conferences now that are done on a fairly regular basis The only thing they can do in terms of coordination exercise has to do with civil defense kind of things, where if something is going to be dangerous, then we can coordinate with each other, at least in information providing, if not in executing some activities that are planned. So those, they have working groups, they have conferences, and then fortunately, we are looking ahead and saying, how can we deal with a potential threat if indeed one is there by our calculations? How can we mitigate it? Which simply means, how can we keep that thing that's going to hit us from staying on that course? How can we change its course? And so that's what the whole planetary defense mitigation mission is. And the current DART mission is the first spacecraft that's actually been launched to address one of the techniques that's been thought about for mitigation, known as kinetic impact, which is, intuitively obvious. You hit something as hard as you can, and hopefully that kinetic energy, that momentum, will change the momentum of the object you hit enough that you'll change its velocity vector and change its orbit. So we're going to test that out, and we'll get to that in a second. First, I wanted to remind you of the threat. When I talked about NEOs before, you may remember there was a picture at one point that was an animation showing you the growing number of the count as different surveillance systems came on board in roughly the last 30 years. And the count went up just astronomically, or almost exponentially, to get to over 500,000, which it is now. And this is a different kind of a chart about the threat. I mean, that was one way to look, and what you see is that the count goes up by leaps and bounds all the time still. This shows you which of those near-Earth objects have actually impacted us over a 33-year period from 88 to 21. And if you counted them, you'd probably find there, in that 33-year period, there are probably about 10 a year on average. And the legend tells you simply that the smallest blue ones are the smallest part of the scale up to the big red one. And yet the scale is just the threshold above 0.1 kilotons. And since that's a fraction, you might think, oh, 0.1, but it's a ton's 2,000, a kiloton's 2 million. And so 0.1 of that is 200,000 pounds of high explosive. So each of these 300 plus in the last 33 years, roughly, has delivered that kind of an explosive energy when that fireball exploded, or I think in some cases they actually hit the ground, perhaps in the water maybe. At any rate, the one that jumps out is the one that you may be familiar with. We've talked about that too. That's in the center of Russia at a place called Chelyabinsk. And so that one was very large, the largest of those over that period back to the 80s, and was about a 0.5 megaton equivalent explosion, which fortunately was about 20 or 30 kilometers in the air, and also not over a population center. It did result, even at tens of kilometers away, in hundreds up to about 1,500 casualties, mostly from the shock wave breaking glass. And so it was pretty devastating for casualties, and by far the biggest thing in that time period. And yet all these others are pretty big too. And so they do happen a lot. Another way to look at what's in the inventory of the known threat is to kind of start at the right here and look at the very biggest ones that we count, because there aren't many of them. And that's the 10-kilometer class. And the reason that we can estimate that there's one of these every 100 to 200 million years is because we actually have that data point. The dinosaur killer that you recall, about 65 million years ago, which, as it says under the impact there, was actually globally devastating and wiped out, extincted many species at the time. And had we been alive, probably it would have been the end of our species too. So that's that particular large category. We have in the inventory 4 known 10K size excuse me, objects. And we believe that we have 100% of them accounted for in terms of what's up there in near Earth space. And the reason we feel confident in that estimate is for the simple reason that they're really big and not hard to find at all. The next class down, we worry a bit more about. They're a kilometer, and they're going to have a devastating effect if they do, in fact, ever get into an airburst or a ground impact situation. And while it's not estimated that they will cause worldwide casualties, it is estimated that given our infrastructure, that, thank you very much. Much appreciated. It's estimated that it would cause so much devastation, much like a very, very large CME, coronal mass ejection, to our technological infrastructures and navigation and communications and information capabilities, that it could very much lead to the collapse of civilizations that size of a detonation. We think we've found 90% of them, but that's kind of scary when you think that that means there's maybe another 100 up there that we haven't found yet. And so we're looking hard to fill in that gap. The next size down are still pretty dangerous. 160 meter, we actually have some examples of things approaching that in our history. And in the impact database, it's online for you to look at. The couple hundred craters we've found around the world relate to all 3 of those larger categories. There are only 3 that are in the category of the 10 kilometer, but there are quite a number in this 160 millimeter, or I'm sorry, kilometer size. And as it says, they will cause, major casualties, especially if they're over a population area. And the trouble with them is there are so many of them. And while we found, we think, over 8,000 of them and put them in the inventory, we think there are at least that many more, maybe 12,000 more that we haven't found yet. So we're looking hard for those. And then we get to the lower sizes, which in the case of 25 meters are still pretty dangerous. And we've got a couple fairly recent examples of those. We estimate the frequency to be about 1 every century. There was one we've talked about in Siberia, fortunately in an area that had almost no people and lots of trees that got blown down in the early 20th century. And it was so sparsely populated and unknown that it wasn't actually witnessed by people except some of the indigenous there. And when they actually went to study it about 2 decades later, it was just getting sort of some folklore and counting trees blown down and identifying ground zero. But they were able to estimate the size of it, and it was pretty devastating in terms of the impact. And had there been people there, it would have been quite devastating. And that once a century got tested when we had the Chelyabinsk almost a century later, just 9 years ago now. And so it was a little smaller, but it could have been much worse if it had actually been over a major urban area. And
so
then
there's no crater from Tunguska, right? No crater.
They were not able to identify one. The scientific expedition got there in 1932, I think. So by that time, they really had trouble, finding physical evidence of it other than the trees lying on the ground. The last one I'll just note here is kind of in between those lower 2 categories. And any of you that have traveled to Arizona might have had a chance to look at the Behringer Meteor and the Meteor crater there in eastern Arizona. It's well identified by signs on the interstate. It's only a few miles off, and it's a great thing to go visit and look at into this very large crater, very deep crater, and maybe buy something from the souvenir shop or the snack bar too. So it's kind of an American way of seeing what a NEO can do. Now, it was a metallic asteroid that hit at a particularly steep angle, which is really devastating. And the rings here show you that the fireball actually had an impact out to about 6 miles, so nothing would have survived. Nothing living would have survived in that. And out to about 15 miles, you would have had lots and lots of fatalities and many more casualties, and hurricane force winds out to about 25 miles, which probably takes you into New Mexico at that point. At any rate, that's interesting. It was an area prehistory, so you can't think about its impact on humans so much, but if you put the same scale over a metropolitan area, then what you get is this. If it happened to have ground zero in the middle of District of Columbia, then the fireball would essentially kill everybody in the district. And we won't pause and think about whether that's good or bad. We'll just move on to the fact that well into the Maryland and Virginia suburbs, you'd also have lots and lots of devastation and hurricane force winds all the way out to the Chesapeake Bay. So these things, and that's a 50-meter impact, and we've not found by any means most of those. There are lots and lots of those up there that haven't yet been identified and tracked. Now we're going to pause for a minute from thinking about the threat and thinking about what to do about the threat. So if you look at this graph on the right, the y-axis is the same scale that went left to right with the sizes there, from 20-meter diameter up through 1 kilometer there in about the middle of the chart, up to the dinosaur killer, the 10K at the top. And so these are the general categories that have been studied now for a couple decades of what we do about stopping one of these or moving one of these off of its path if it comes to that. And one of the bad news things on this slide is for all those roughly 1 kilometer and above, there really isn't any technique in terms of delivering enough energy to change things other than nuclear that we know of. And there are, as we said, 900 known at this point, and at least another 100 that we're likely to find. And so there are quite a few of them. And nuclear isn't necessarily good in that it's uncertain as to whether you will just exchange one huge devastating impact for several, maybe half a dozen large pieces that will also have an impact on Earth. So we may end up just multiplying the problem rather than having it go away. So in the area that we hopefully are going to learn to do things about, between about 100 meters and 1 kilometer there, the two techniques are quite different. The tractor we talked about very briefly before, it's basically to send a large spacecraft, maybe more, I don't know, out and park it literally right next to the potential dangerous object, which you've projected to have a time of at least a decade or two before it's going to go around and it's eventually going to have a collision with the Earth. And so you park a tractor next to it, and the mutual gravitational attraction over a period of years is enough to pull it slightly off of its trajectory, change its velocity vector just enough to miss the Earth. That's the idea. Certainly theoretically it can work. It'll take a long time. And as you see from the fact that it occupies the long forecast period there of 20 years plus on the x-axis, it doesn't fit everything. If you've got things that you project to come in closer than 20 years and they're bigger than 100 meters, then you want to have a technique, and that's where we fill it in with kinetic impact. And we haven't done it yet. And so the whole idea that was addressed by the National Academy of Sciences a little over a decade ago was to recommend that that be the first area that we do an actual test of. And so NASA picked that up. They got the program funded, hired APL, and now DART is going to test the 160-meter size asteroid with a kinetic impact coming very soon. And now we're going to get to that. So here's the target. And we don't have time to go into how they chose it, but as you can imagine, it's an identified asteroid in near Earth space that we can get enough information about to know what the impact of our impact was, or what the result of our impact was, to learn things about kinetic impact. It is, in fact, a double asteroid system. You folks are familiar with binaries. And so the big brother is Didymos, which is, in fact, very big. And we aren't certainly going to try to hit that. That's in the category of global devastation. What we want to find out is what we can do with kinetic impact in this 100 to a few hundred meter range. And so the little moonlet orbiting Didymos is Dimorphose at about 160 meters. And so that is our target. And just to give you a feeling for the scale, the largest dimension of Didymos is taller than the World Trade Center and approaching the largest skyscraper, and by far more massive than either one of those. And even Dimorphos is, in its linear dimension, bigger than the Statue of Liberty. And as far as its massiveness, it's about like the Great Pyramid. Picture it like that. So it looks small because it's sitting next to its big one, but it's very big. Another way to visualize it, I picked up, I really like this one. There it is hovering over the Colosseum, if you've ever been there. So it's not small at all. And it'll have a target on it. It does right now. And what we're going to hit it with is the DART spacecraft. So this gives you a feeling for just how big DART is not. Okay, there's a dimension of it. It's taller, or it's longer than a school bus is long, shorter than the Arc de Triomphe. And as you'll see, most of the mass is right in the center when we take a look at it. But it is what it is, and we've gotten it up there, and it's on its way. And its target is that fixed object that the Very Large Telescope in Chile is imaging here as the stars pass by, as the Earth rotates. And so there we have the best pictures that we have. Now, many ground-based telescopes have taken pictures of it, but at its size of whatever it was, 700 meters, something like that, it's not large enough. And the two are so close together that they certainly can't be resolved. And we haven't even got a good optical image of it. The thing on the right there is what we think it might look like, but that's not an optical image. That's a radar. It's based on radar data, and it's based on the light curve data that you'll see how we use that in a minute in order to establish the period of the smaller object around the larger object. So it's roughly that kind of a shape, we think. And as we approach it soon, we will finally get some up close images of it. So that is the target, Didymos, the moonlet. There's what we know about it in between the two question marks there. We certainly haven't seen it yet, but from the light curve data, we know it's there, just like we know the exoplanets are there. And we've been able to estimate its dimension, and we've picked a number of examples of that size range of different asteroids there. And so we've come up with this as our guess for what Dimorphos is. And coming in September, we will actually be watching as we find out what it really looks like. But I wouldn't be surprised if NASA does their media coverage the way they seem to be doing these days, if you don't start to see the picture of Dimorphos there and have people thinking of it that way, even though we have no idea what it really looks like at this point. but that's our target. So I thought at this point it might be useful just to show you a video starting with a launch, which took place at the opening of the window from Vandenberg, which you note now is not an Air Force base, it's a Space Force base now, on a launch site just a few hundred yards from the Pacific Ocean at the end of November. And so here it is being launched on a any minute. There we go. Being launched on a Falcon 9, coming off the top of the second stage and unrolling about, let's see, about, I think about 30 feet of solar panels in both directions, uncovering the very important camera telescope as it approaches this system, which is coming around in its 2-year orbit to be right close to Earth. And just before, 10 days before impact, a CubeSat will be launched to take pictures right after impact. So we get a look at the crater initially. And here is an animation of how it guides itself in. We'll see a bit more about that in a minute. And so that's a good, artist video of the whole thing. So here's another way to look at the system. It kind of looks like two objects there, but that's actually Dimorphose as a bilobe kind of object that we picked, orbiting Didymos, a little less than 12 hours period. And that was the period today. Now DART will come in, the LichioCube CubeSat will be deployed, the impact will take place, and the CubeSat will take some pictures. So that's the essence of the mission right there. And the first and very important measurement to be taken is to see how much we changed the momentum of the target object. If we changed it as much as we expect, it could be many minutes shorter than it was before. And so the same technique that's been used to use the light curve to estimate the current, estimate very precisely the current period, will be used right after this. And so we'll get a chance to see that we did in fact have a measurable influence with our impact. So the first requirement, which hopefully will be met at the end of September, probably right at the beginning of the window, there's a several-day window, will be on September 26th. And the next two things have to do with what I just said, changing the orbital period and measuring that period from ground-based telescopes. And then finally over here, the fourth requirement is to calculate something that's extremely important. This has a lot more to do with actually how effective any kind of kinetic impact is going to have on an object, because we don't understand that much about these small solar system objects in terms of how dense they are, how hard the surface is. We only have a few examples so far. This is a model of what we call a rubble pile asteroid. And we believe all of these, including even Didymos, are rubble piles, basically very small rocks, including some dust, up to much larger rocks and some boulders maybe, all held together by their own gravity, which is to say that the smaller they are, the smaller the amount of gravity holding them together is. And so this is a NASA model of a crater being formed by an impact where the impactor excavates material in the opposite direction. And just like Newton with his third law tells us that there's an equal and opposite reaction, the ejecta will actually increase the velocity change in the other direction. So part of the oomph that we're going to get from hitting it isn't just from hitting it like a billiard ball would hit a pool ball in an elastic collision of two hard objects. It's going to be to eject a bunch of material. And so that measurement of beta is very key. So now let's look at that period of Dimorphose. And you're familiar with these light curves, I think. Very accurate measurements of the sum of the light from the two objects, and then the change in that, the decrease as the object passes in front of or behind, and the ability to time this and use repeated observations to get more and more precise estimates of the period. And today the period is something like 11 hours, 53 minutes and some. And you see the reason why it's kind of offset there as it goes behind is because the telescope's shown on the Earth over here to the right. And in fact, all of these telescopes have actually imaged and measured, estimated the period. So it's been done a number of times now. And my guess is if you went to any of these in the middle of September, you'd find that they're all signing up for a pool to see who in the competition will measure an accurate period change first. And so I'm really excited to see what they come up with, but they'll all be trying to figure it out. So that beta that I mentioned, just to show you in one example here on the left, if the impact hits a surface that has no crater formed and no ejecta, then that's a beta of 1. The beta is sort of the additive part in addition to the momentum, where mv, the mass times the velocity for a very small mass with a very high velocity, is hitting a very large mass with a small velocity in this case. So you get some momentum change, but beta is the extra momentum change. And we expect something more like cases middle and right there, where if you get some ejecta, you get a higher beta. And if you get a lot of ejecta and a big crater, then you should get quite a bit of extra impulse, extra push from the ejecta. So we'll see. Again, they like to model things. And so this just gives you an example with their rubble pile model of all these different sizes and shapes of the crater being formed and the excavated material being ejected out. Now, I kind of went away from the presentation we were given to look into something that just had a study announced last month, and that was the Asteroid Bennu. And some of you may remember this in the news maybe a year and a half ago. A NASA spacecraft called OSIRIS-REx visited Bennu. Here's how big it is. So it's in between Dimorphose and Didymos. And it's in between, as in quite a bit bigger than the target that we have. Okay, try that again. And 25 times more massive than Dimorphose and much higher gravity, because that's what's holding the whole thing together. And so we actually did visit it in October of 2020. They rendezvoused, they orbited, they picked a spot to touch down, and they did an event called a TAG, touch and go. And I'll give you a look at that in just a minute. But my point in looking at this and comparing it is, that's a much larger object that we just learned something about by literally going down and hitting the surface and learning something about the surface layer with quite a bit higher gravity than Dimorphos has. So let's look at what they found. There's a picture of the spacecraft as it was going down with its foot called TAG-SAM. It's a sampling technique with a touch and go. They didn't collide. They literally came to the surface at the velocity of an insect walking, is the way they describe it. And when they pushed down on the surface, they blew a puff of gaseous nitrogen, a large amount of it, that caused the material not only to excavate a crater underneath them, but to blow the material up in the air. And you'll see that in the video in a second, and collect the material, which has then been put into a re-entry vehicle that's on its way back to Earth, and it'll arrive next year so we can actually study the material. They've got about 1/2 pound of it. But the big surprise, and this is why they just had, even though this was all done in 2020, a study just came out in June and was in Nature, and and I saw it on space.com, that shows that they revisited it after the initial mission, again, went back and got better pictures of the crater. And they have found that the depth and size of the volume of the crater is much bigger than they expected. The composition of the surface, they believe, is quite a bit different than they expected. So I'm going to see if we can get this video to run here. Let me give it a try.
One of Earth's closest neighbors is a dark, jumbled mass of rocks and boulders known as Asteroid Bennu. Bennu is ancient, a rugged survivor of the solar system's chaotic past that may hold clues to the origins of life. In October 2020, a NASA spacecraft called OSIRIS-REx touched down on Bennu and collected a sample for return to Earth. Scientists had expected that this touch-and-go event, or TAG, would have little impact on the asteroid. After a slow descent, the sampler head would briefly make contact, inject a puff of gas, and capture a handful of material. Perhaps it would also leave a small divot at the sample site, a subtle footprint in the soil, or so it was thought.
So that was just an artist's concept. Here are real images.
Far more dramatic than anticipated. Despite its slow touchdown, OSIRIS-REx had punched through the surface and set off an explosion of loose material. Tons of rocks and pebbles were ejected, radiating outward in a wall of debris.
The crater is like 8 meters wide.
The surface behaved so unexpectedly. The answer involves cohesion, an attractive force that can bind molecules together. Cohesion gives water its surface tension and keeps droplets together even in a microgravity environment like the International Space Station. Granular materials like wheat flour, cocoa, and dust can also exhibit cohesion, which pulls individual grains into clumps. On Bennu, scientists had expected cohesion to act like a bit of glue between the rocks, making its loose surface more solid. But the TAG event showed that Bennu's uppermost layers are nearly cohesionless, deforming under stress like a fluid. A good analogy is a ball pit. Although the plastic balls are solid, they easily slide past one another and past boisterous children, behaving in mass like a fluid. Thanks to OSIRIS-REx, we now know that Bennu's surface is not held together by cohesion, but by gravity, or microgravity, with a minute tug less than 100,000th the pull of Earth. On the Moon, gravity is 16% as strong as it is on Earth,
How do I stop
and more
this?
than 16,000 times stronger than it is on Bennu. As a result, loose material in the lunar subsurface is packed together more tightly, making the surface relatively.
Okay. That's
Earth's closest neighbors is a dark, jumbled mass of rocks and boulders. No.
Here we go. Okay. What I wanted to emphasize here, you may have already gotten it, but it's quite simply this. With the microgravity of Bennu, remember being 25 times more massive than the target we're about to hit, the surface was so loosely packed that it behaved like a fluid, is the word that they use. And so the model that we saw before, that APL has shown us, of what might be a beta from some excavation of a material, I'm eager to see what happens, because it looks to me like with this sort of surface, you're more likely to get the effect of a crumple zone on a car, where much of the energy is simply dissipated in the surface and in moving around things that aren't really being held together by much. And I'll be very interested to see what we learn about how much actual extra momentum transfer we get from this. All right, so let's see. So here is the spacecraft. On the left there, you see one view of it, about 8 to 9 feet tall, very simplified views. The things that matter, that telescope that's going to be used to find it and then guide the impactor in, the CubeSat that is going to be deployed from the side there. If you flip it 180 degrees for the middle picture, you see that you guide it with a combination of software and the telescope's images and these hydrazine thrusters that you'll see a simulation of in just a minute. And the other key component I wanted to point out was that high gain antenna, so that we're going to get to witness this thing in real time as it moves in.
Question,
Yes.
what's its main propulsion system? Is ion thrusters?
That wasn't its main propulsion system, but yes, you were right. That is what that video showed. Yeah, there was an ion system that was used.
Because you don't get a lot of thrust.
No, you don't. And you only use that when you're in space with a lot of time available to get somewhere. And in this case, since we just launched it in November, we didn't have a lot of time to get anywhere. So they're just kind of testing out that ion system on this vehicle, but that isn't the main.
So the hydrogen you make, is
Yes.
that a mono? Or
That's a good question, and I don't know. So the big dimension that has little to do with the mass is unrolled solar panels you can see there. So it's 60 feet long, 30 feet each, and with the mass all concentrated in the middle. To give you a better idea of the size, here it is, and you see in the upper left there, it's about 1,500 pounds, which is about the size of a smart car. So picture a smart car with wings, and that's kind of the idea. Or you can picture Shaquille O'Neal standing on the ground next to it and putting his palm on the top of it. That's how tall it is. And now I'm going to always have a picture of about 4 or 5 Shaquille O'Neals impacting the asteroid. But at any rate, that's what's coming with DART. All right, so the other main performer there, a spacecraft in itself, is built by the Italian Space Agency named Licia Cube. And I like to show the size of these standard CubeSats, because you may know the 1U is well defined as about the size of a Kleenex box, okay, about 4 by 4 by 4. So if you stack 3 of them next to each other and another row on top, that's about how big Licia Cube is, with its solar panel wings there for power and its 2 nicely named cameras there. I guess the Italians liked Star Wars. At any rate, what I do note here is that not only will it be deployed early, about 10 days before the impact, but it's timed such that it will take the pictures about 3 minutes after impact from up close. But the best resolution they're going to have is 2 meters per pixel. Well, I mean, 2-meter resolution to look at ejecta on the surface and things like that is going to be lucky to tell us very much. Now, I'm eager to see it, but we don't get as much primary data about what happened to the asteroid from this camera as I wish we would, but you'll see that we've taken care of that a different way. So here, in fact, is how the operation will go. That Draco camera has an acronym there, Didymos Reconnaissance and Asteroid Camera, for OpNav. And what I thought you folks would be more interested in is it's about an 8-inch aperture. And that's what we have to give us the best possible images to find and then keep an eye on, literally, the target as we move in. And so here is the sequence of events. Late August, about 30 days beforehand, is the first we expect the Draco telescope to be able to identify the Didymos system. And it'll be at that point that we actually start to get some images and see what it is that we've guessed about the larger body and what its shape actually is. But it'll be quite a ways after that before we can see the smaller body. About 3 weeks later, they'll have the ground or the coverage for the high gain antenna there on continuously for the last 10 days. So we'll get to keep an eye literally on what it's seeing all the time. And then in the last day, we get down to the last 4 hours and they enable the SmartNav guidance system. And you'll see a simulation of that in a second. So clearly you want to tie the imagery together with the thrust control mechanism, the hydrogen thrusters, with some very good software, which is the SmartNav system. And so that gets going 4 hours beforehand. And in the last hour, I think it's kind of interesting to see that it's going to be about 15,000 miles away. And so that's an hour. And so you now know that the relative velocity of the impact will be 15,000 miles an hour when it hits. The time is, coincidentally or not, correlated to the resolution of Draco, in that it's the first time they believe they'll actually be able to fully resolve with more than 1 pixel of that little moonlet that is the target, Dimorphose. So at this point, we hone in on it, and we get, as you can see from the inset, the yellow there in the center, that's the actual data that will be telegraphed or will be telemetered down to Earth that we'll be able to see. And you see the hydrazine thrusters firing, and they keep the double asteroid system centered. And we've got a simulation of the last hour here, speeded up at 30 times. But even at that, I'd like to go ahead if I can get it moving here. Let me see. I'd like to get down toward the end. No. Yeah, here we go. So now we're still with a fast animation. Hard to read the numbers. No, that's still 54 minutes, isn't it? You know what I'm going to do? This is one of those times where you wish you were using your own computer. I'm not going to try it. Never mind. It'll be over. It's going to take about 2 minutes. I just want to take it out of slideshow mode for the moment.
We'll lose it on the main screen though.
That's all right. Yeah, I can't do that. That's what I've been trying to do.
Okay. Can't.
Yeah. All right. Well, if this were, if that were working the way I wanted it to, you'd see the screen eventually fill up as it centers it and impacts it. And then we'll get a chance to see up close what it actually looks like as the spacecraft goes in for the impact here. And hopefully kicks off a lot of ejecta and leaves a crater for the Lichia cube to take a look at, even though its resolution's only roughly, what did it say, 2 meters per pixel. All right, so now I'm going to tell you why things aren't quite as bad as that, and I should maybe say it in such a negative way, but I was hoping for better resolution. The mission is actually an international mission known as AIDA, which you see the long name for up there, and it's done jointly with our European Space Agency partners. So the first part of it is in fact the impact by DART, and the second part of it is a European Space Agency mission that's going to do a much better job of actually reconnoitering the site. It's not going to launch until about 2 years after the impact. It's of course headed for the same target, Dimorphos. It's going to get there and not impact it, but rendezvous with it in 2026. And it's going to do a crime or crash scene investigation and do a much better job of measuring the mass and the details of the crater and the ejecta. And the way it does it is with thermal imagers, optical imaging, LiDAR, which is great as you move around to actually see the shape and the topography of things, and some CubeSats, and they're still deciding how many to have, that will go down at least close to the surface to take their measurements and may in fact land on the surface. So the best of the data that's going to come out of it in terms of what the actual impact caused on this particular kind of a surface isn't going to come until 2026, unfortunately. But that is the way it is. It's a coordination of 2 planetary defense programs. And so we'll get some good information this September and better information hopefully a bit after that.
Hey, John.
Yeah.
Did you tell us this already, but how far is the target from the Earth and what's the speed right now?
The target, let's see, the dual asteroid system has a 2-year period and it, you know, crosses Earth's orbit. So you can calculate the speed. The distance was selected so that we could have a launch that would have it arrive when it's at its closest approach to Earth. And I don't know what that is. Okay, sorry, it's a good question. The answer is I don't know.
John?
Yes.
On YouTube, Howard Goldner was asking, the lack of cohesion on Bennu, is it possible that on the smaller target that it may well just be that the impact will be just absorbed into the mass of the object and have no effect?
Nobody in our ambassador group was so bold as to ask that question of the scientist who just spent years preparing for this. But I say that I actually didn't think to ask the question. I just got this data about Bennu about 2 weeks ago and just added it in. The information we got from them came about 4 months ago, which was about 3 months after launch, I think. I imagine, I mean, they're all one small, tight-knit community. So this is going to be the first data point for a particular mitigation technique, and they are all eager to learn about 160-meter class potentially hazardous asteroids as to whether or not we're going to have much impact on them at all, unless we can get a spacecraft up there that's, you know, many tons, let's say. But they're going to learn a lot about the surface from this thing. And I'm afraid that what we just read about Bennu that was just published is a bit scary in terms of how much energy absorption there's going to be in that surface area, as opposed to just
Maybe you need to go in
translating. Yeah. So I'm not
Did they do
quite.
that in Spaceballs? The giant vacuum cleaner.
So I'm going to finish up here with a famous rock group that you probably recognize. There's Queen. And some of you may even know why I've got it up there, because this guy, Brian May, is their lead guitarist. And you may or may not know that he's also a famous astrophysicist, very involved in the NEO program. And the reason I'm showing you this is he's the narrator, looking like a century-old English barrister here or something, as he looks today, narrating a really great video about the European Space Agency's program. So I've provided this slide among two to Jeremy so he can circulate them. So you don't need to write down that website. If you want to look at this video, I really recommend it. And then finally, the other slide that Jeremy's going to have for you, since you guys love to do, not necessarily looking through the eyepiece, which is suggested by the Minor Planet Center here, won't be very satisfying, but with some astrophotography, you may get a chance to actually see it in the window of impact down there. It's very much at the southern end of Eridanus, kind of below Orion and Lepus and to the right of Columba there. So it's very much in the south, but that's where it'll be on September 26th and for a few days after that, if you want to try to get a picture. And nobody's suggesting you're going to see the impact, just if you want to get your own look at this dual asteroid system. So thanks very much. More questions? Go ahead.
So the Draco system, is that going to be,
the Draco system, is that a visible camera or is that something else like infrared?
Nobody asked and I didn't, so I don't know.
Okay.
And I haven't seen the specs on it. All I found in the specs was that little bit that I showed you there about its aperture and everything.
Okay, yeah, yeah, I'm just wondering, is it visible when they'll have to take into account? Is this thing gonna be illuminated to see it from sunlight? So, okay, thank you.
Yeah, I have to assume with all the planning that goes on with these things, that folks are planning that in, or that they've got a thermal capability, you know, so that, you know, having once done some research into the infrared signature in the Nevada test site from nuclear detonations and the changes in the surface layer, I know that it's much better to have some thermal IR for that. Yeah. So I don't know. It's a good question. Anybody else?
Thanks again. Nice presentation. I know you mentioned it, but what was the velocity that the darts when it hit the
15,000 miles an hour.
15,000 miles an hour, and the mass of
The mass of what, Dimorphose?
no dart.
Darts is 1,500 pounds. Yeah, not very big.
Thanks.
A smart car hitting the Great Pyramid, in Egypt. Yeah, and I don't think
smart car going very fast.
that's the key. And hopefully not having all those plastic balls spread readily. Nothing.
It's interesting that you mentioned that the ejecta will actually fall back on it and further the momentum of the.
It's not by falling back that it furthers it. It's just, you know, a rocket engine sits here and the rocket equation basically says, how fast can I exit how much mass in the direction other than where I want to go? So that's the action and that's the reaction. And in this case, the action is all that material going one way, which is back toward where the impactor came from. And the reaction is pushing, giving some added velocity to the body. Yeah, that's beta.
Question. Realistically, how big an impactor would you need to be an effective planetary defense weapon?
I'm not smart enough to answer. It's early days. Obviously, this is the first actual empirical data we're going to get from trying to do something and seeing it with enough detail to see what, I mean, it's all about the surface layer and the composition, not just the concentration, but the composition of the object that you're hitting. And we do not understand small solar system bodies very well. Yes, sir.
Has anyone looked into the effect of the gravity produced by Dimorphose on the results of your experiment? In other words, Dimorphose itself has a certain amount of mass that's holding the little guy in orbit. So some of that gravitational field, those effects are going to influence the actual results and make it different from the case where you're just hitting that smaller asteroid by itself.
All I can say is my gut feel is that that's very much a higher order effect. I don't think it would have much effect on it personally.
Okay, sure.
All right, other questions? Maybe I have one.
Okay.
How transferable do they think these results are? Because maybe, you know, some asteroids have different compositions. So, you know, is this one picked out for being really average, or do they think this one might be better or worse? Because I think, you know, it could be like a rock. You know, you can kick a rock and you can send it, or you kick a pile of dirt and it doesn't really go anywhere. It's a, you know, how strongly cohesive are they, and you know, how heterogeneous is this class of objects?
Yeah, I mean, the example that I keep coming up with, I think that through is, you know, simple pool table, and you want to put the 8 ball in the side pocket, and you get an almost perfectly elastic transfer of momentum from the cue ball. And so the rest velocity of the 8-ball becomes almost the same as the velocity of the cue ball that hit it. Now, if you happen to make, have a trick set of pool balls, to entertain your friends with at the bar or something, you might make one of them out of something that looks like it's solid, but it's made out of clay. And watch as the front half of that just pulverizes, It could be more like that, I'm afraid. Looking at what they have found on Bennu now, that mass, that was tons of very small material that literally got ejected over, a 25-foot radius from just that single touchdown and blowing the nitrogen out there. And it made a much deeper crater than they expected, but it spread this material all around. And I think, much like a crumple zone in a car, it probably kept most of the asteroid from feeling much of anything. But of course, you don't care if the asteroid feels it as long as it changes its momentum. I think they've kind of put the whole group of ambassadors into the situation of we can kind of all think this through. We throw a bowling ball down and hit a pin and watch as, the ball slows down and the pins pick up the velocity where they're just sitting there. We can all picture these collisions. And the big mystery is beta. The big mystery is and beta is a function of the surface layer, density and cohesion, and what lies underneath it. And we can all understand for the uncountable number of asteroids of this size that they aren't all going to be alike. But the sooner we start getting some data points on what seems to change, and we'll actually have an estimate from the change in the period of how much, velocity change there was. As soon as we get some data points, we'll start to be able to guesstimate whether the mass, if it had been 10 times as much, would have caused this much of a change or something like that. But more and equally important, understand what the surface of these small solar system bodies is like. Because while they may be lacking in cohesion like Bennu turned out to be, when that mass comes through the atmosphere and most of it hits Earth, that's devastating regardless of what the surface was like.
John, Lou Berman asked the question, is there anybody that's extrapolating how much energy we would end up needing to deflect something? I guess in the 10 meter, 100 meters envelope. We're obviously just doing an experiment to gain some initial knowledge, but do we have an end game?
I would be very surprised if they don't have plenty of curves that have been debated and put into papers, and that they're waiting for the first actual data points, and that we've been talking about the coefficients like not, the properties and coefficients, density, surface cohesion, things like that, to actually get some data points to start to test their equations and see if they can estimate these things or draw some curves, do some scaling. I imagine the debates are a lot of fun, actually, but we're going to learn a lot with this, I think. I just wish we had better resolution to see it initially instead of 2 meters per pixel.
Thank you.
If it's successful and you're able to change the orbital pattern, I guess, of Didymos, does it also change Dimorphos a little bit?
No.
No, not at all.
No. No.
Much bigger.
No, yeah, much bigger. Bennu you saw was 25 times bigger, and Dimorphos was another 200 meters, 300 meters in diameter bigger than Bennu. I imagine that the mass of Didymos is at least 100 times greater than we could calculate it pretty easily, but at any rate, yeah, no, there's not expected to be any appreciable change, no.
And then in the future, like if there is an asteroid and it's got our name on it, like we would need to approach it as early on, because that way the smallest change in deflecting it equates to a much larger degree of difference.
The more decades
right.
before the predicted impact,
right.
and the more of those decades we can have left after we've done something to try to change the velocity vector, the more change there will be by the time that collision might have occurred. Yes.
Actually, Mitch's question brings up an interesting point about scaling, right? Because you look at the two objects, one is like, oh, it's 10 times bigger than the other, but it's 10 times bigger in one dimension, 10 times bigger in another dimension, and 10 times bigger in the third dimension, right? So that's cubic scaling. It's 1,000 times more massive. And that's probably about it. I think the big one is probably about 1,000 times more massive than the small one, or a couple hundred.
Yeah, it's certainly a lot less.
Things get big real fast.
They also found with Bennu, I just remembered this, I was going through the paper today, that the density of Bennu was about half of what they'd predicted. That's a very large asteroid. That's a pretty big deal.
So I would suggest that it's very loosely packed.
Yeah, yeah. And Dimorphose is a lot smaller. So, you know, I just don't know what they're going to find when they hit the
good masses if it's an orbiting system.
That's an interesting point. Yeah, there's some angular momentum. It has to
affect the orbit of the smaller object orbiting the larger. Would it be possible to affect that orbit so that it crashes into the?
I mean, that's, let's say we could, the probability of that being the one that looks like it's going to be a problem is small. I mean, the double asteroid system with a much bigger and a much smaller, and it's the small one we think is going to hit us, even if we could do away with it by that technique. It's kind of an interesting thought, but you're not going to run into that very often at all.
Also, you mentioned that you ran this and there were no, for decades, there were no near miss objects. Did your projection say when there would be one?
The
potential?
Yeah, of course, I didn't run it. I mean, I'm just telling you what NASA has, and the Minor Planet Center has it too. But the easiest way to look at this, and you can look at it anytime you want to. Do any of you look at the spaceweather.com website? Okay, all the way at the bottom of that, at least the other day, they have all the NEOs that are projected to show up in the next 3 months. Anytime you want to, there's a real-time changing list of the next few months near Earth objects and what their miss distance from collision is in terms of lunar distances, 250,000 miles. So if you see 4 LD, then that's about 1 million miles it's going to miss by. There are very few that are under 4. Once in a while, there'll be one. Once in a while, there'll be one that's half, but that's still, you know, 4 times as far out as the geostationary spacecraft are. So you watch that column to see. You also watch the size column, which is one of the other columns in this table that, again, changes in real time. Every day, the list is slightly changed, okay, looking a few months out, is the size. And so it's the estimated diameter. And so you find all these that are 12, 20, 6, maybe there's an 80. Maybe once in a while there's 780, or there's one that's 1.5 kilometer. And so there are some pretty big ones that show up rarely, and you find a big one and you look over at the miss distance and you find that it's going to miss us by 4.3 million miles. Okay. So there's no combination projecting all of these hundreds of thousands of objects out for decades that is going to cross Earth's path at a point in time, anytime in decades. They haven't found one yet. They found a few that maybe 34 years out or something look like there's some percent of chance, maybe 2%, that it might become within an envelope of distances that would be worrisome. So they'll keep an eye on that and update it after a few years.
How about centuries?
Well, you could do it. You can do any of these calculations as long as you want. They're kind of meaningless looking out. I would suggest. I used to do orbital mechanics all the time. If you look out 100 years, there are almost certainly going to be some perturbations. You know, whether it's Umama or one of these minor planets or something that comes from another star system that comes through, or, you know, just changes in for whatever. There are different reasons. The trying to remember the name of it. There's an effect due to solar radiation or solar radiance. Basically,
Pointing Robertson.
Excuse me.
Pointing Robertson.
No, that's not the one. Sarkovsky effect, I think it's called. And it basically is saying, and the choice that they made of Dimorphose being a bilobe object of irregular shape and size. In that case, if you picture an asteroid for many years sitting out there with solar wind hitting it, the different sizes of it will cause rotation because there's actually pressure from that solar wind. And so that can actually cause a perturbation sometimes, not just in the rotational period, but actually in the position of it, in the velocity of it. So that's a kind of a perturbation that they look at that takes a long time, but nonetheless it's there. But back to your main point, we haven't found anything yet that's in that catalog. I'm trying to remember the name of the website. I'll send it to Jeremy, but it's a NASA website, NEO something or other, CNS or something like that. And it has a headline, you know, it's got a pull down menu and there are headlines. So if anything is coming close, there'll be an article about it there. But it always has this list of potential of nearby NEOs, basically, updated all the time. And you'll know about it within 24 hours if they ever find one that, say, is dangerous, big enough to be dangerous, and has any finite probability of hitting us within the next decade or something like that. That'll be big news. So far, nothing's even close to that.
I'm just worried about my great-great-great-great-grandkids.
And we all should be, in all seriousness, which is why investing in this mitigation program is really important, I think.
I wonder if any of these, you know, they have the surface, gravelly surface, but I wonder if any of them have solid cores.
I don't think that that's what they think. I think they, you know, you picture the asteroid belt and all of the many planetesimals of various sizes in that, and slowly but surely through the first billion or 2 billion years, things close enough actually joined with each other. You remember the one object that we found out in the Kuiper belt and visited was a bilobe. Basically, it was a contact binary. It looked like probably it wasn't really held together, although it was touching. And so lots and lots of the bigger objects collect small objects, and the ones that didn't make planets, like all those that are the asteroid belt, basically a failed planet, just stay all those small pieces and they collect up with each other. But I think most of the collection has been done long in the past. And having said that, there are collisions every year, so things do happen.
All right, any other questions? I just got a comment by text. Best presentation you've ever done. Here.
Oh my goodness.
So it's a pretty, pretty big compliment. Anything else on YouTube? No questions from the internet. You've silenced everyone on the internet. You've silenced the YouTube comment section.
Thank
let's thank John.
To whoever gave me, I want to give 2 thanks. One to whoever made that comment. That's very kind. The other thanks I want to give, I don't think he's in the room, but the gentleman in the pickup truck 2.5 years ago when I had to holler for help down there that helped me. I don't think he's here tonight. I don't see him.
I think that might have been Bill, younger guy.
Yeah,
Paul.
yeah, right.
Was
And
was that January 2020?
yeah,
Because you were the last speaker then before the pandemic.
yep, I was.
As I say, luckily nothing else bad happened that
And
year.
my wife and I got to enjoy being locked down for about 1.5 months before the pandemic locked everybody else down.
All right, let's thank John for a really great talk.
Thanks.
Howard Goldner says, don't look up.
All right, let's switch over to the other camera for a minute. So everyone out there, you are on the internet. So I think this brings the meeting to a close. So we can say goodbye to everyone joining us on YouTube. And hopefully we'll see you next month at Fort Washington State Park. Thanks for attending.